Okay, so in this video, I want to talk about how to solve word problems involving proportions. So classically, when you're dealing with word problems, you'll see the word application, so applications with proportions, or you'll see the phrase problem solving, so problem solving with proportions. Either of those would indicate word problems. Now, really quickly, to review in the previous video, that was video 3 in this series, we would solve a proportion by cross multiplying and then solving using that little tiny bit of algebra I showed you in the previous video. One thing you do need to make sure that you do in this situation where you're dealing with word problems is you need to make sure your units line up horizontally. And I'll show you exactly what I mean as we start this. So again, what you need to do to solve a proportion is to cross multiply and solve. And we're going to set up our proportions, making sure that the units line up horizontally. So with these problems, classically, you're going to be given one of the ratios or rates flat out. All right. And then the second ratio or rate is going to be missing one of the two pieces. And that's how we're going to set it up. We're going to set it up to where one of those two pieces is missing. We'll cross multiply, we'll solve. Okay. So in the first problem, let's just dive in. We have that for every 200 cars sold at a dealership, 22 are brought back for major repairs. We know this flat out. At a dealership, 22 cars out of 200 are brought back for major repairs. Okay, that's what we know without a shadow of a doubt. Now, this particular dealership projects that they will sell 1,200 cars this year. How many cars can they expect to be brought back for major repairs? In this particular set of information, they think they're going to sell 1,200 cars. How many can they expect to be brought back for repairs? So here's how we're going to set it up. We know that 200 cars sold, 22 should have repairs. So we're going to have 22 repairs for every 200 cars sold. Okay. Now, this dealership is expecting, hoping, projecting that they're going to sell 1,200 cars. Since in my first rate, I had cars sold in the denominator, I'm going to make sure in my second rate, cars sold is also in the denominator. That means we have no idea at this point how many cars they should expect to come back needing repairs. So now we've set up our proportion. Units line up horizontally, cars sold are in the denominator, repairs, and I'll even put X repairs. So repairs are in the numerator. And now we have a proportion that's set up. All we would need to do at this point would be to cross multiply and solve. So when I cross multiply, I'm going to multiply those diagonals. So I'm going to get 200 times X equals 22 times 1,200. I do like to see the work. So I like to see your steps, but you could certainly use a calculator for the smaller calculations to save time. So 22 times 1,200. That gives us 26,400. So I get 200x equals 26,400. And then remember in the previous video, when you have an equation like this, your job is to determine x. So algebraically speaking, that means we want to get x by itself. Well, x has been multiplied by 200. We need to undo that multiplication. The way we undo multiplication mathematically, the way we undo multiplication mathematically is with division. And remember, if I do something to the left, I do the same exact thing on the right. So I'm going to divide both sides of this equation by 200. The 200s cancel, leaving me just a 1x. And then 26,400 divided by 200, we get 132. Now, when you're dealing with word problems, never just give naked answers. When you're dealing with a word problem, your answers always need a unit or an explanation. Okay, so we have to go back and ask ourselves, what was X? Well, in this particular proportion, X was the number of cars they should expect needing repairs. So 132 cars will need repairs. And that's it. So once you set up your proportion, solving it is really quite simple. All right. So let's move on. Let's look at another word problem. So for this one, it says directions say to mix 6/7 cups of bleach per gallon of water. So you're mixing up some kind of cleaning solution. All right, so 6/7 cups of bleach per gallon of water, how much bleach will be needed for a 7-gallon bucket? So we know that we need to mix 6/7 cups per gallon. We want to know how much bleach will be needed for 7 gallons of water. Okay, so we would get 6. Let me go back to red. We would need 6/7 cups of bleach per 1 gallon of water. We know that without a shadow of a doubt, that's given to us. What we now have to figure out is how much bleach would be needed for, I was actually going to do that in blue to be consistent, so let me fix that. So we need X cups of bleach for 7 gallons of water. Notice my units line up horizontally. I'm ready to go ahead and cross multiply and solve. So when I cross multiply, I'm going to get 1 gallon times X cups of bleach. So I'm just going to get 1X equals 6/7 times 7. So I'm going to clean it up a little bit. I get X equals 6/7 times 7 over 1. I'm going to go ahead and put this 7 over 1 just so we have numerators and denominators to work with. You'll notice the 7s cancel. So I get that I would need 6 cups of bleach. Okay, remember, no naked answers. All answers when you're dealing with word problems need to have a unit or an explanation. And in this particular case, X was the number of cups of bleach that would be needed for a 7-gallon bucket of water. It's that simple. The hard part, which isn't even really that difficult here, is setting up the proportion. Once you have the proportion set up, everything's pretty easy to solve. Remember, look for the piece of information that is given to you completely. So 6/7 cups of bleach per gallon of water. We know that without a shadow of a doubt. Set up your ratio or your rate in this case. And then for the second piece of information, one of the two values will be missing. No big deal. Assign a variable to the missing piece. Set up your second rate. Just make sure your units line up horizontally. Then you cross multiply and solve. All right. So let's look at another example. Let me get some water. So for this example, we're going to be looking at a map, okay? And we know that without a shadow of a doubt, 2 inches on a map represents 120 miles in real life. So if you're looking at this particular map and you can measure out 2 inches, that's 120 miles. We're then told that 2 cities are 5.5 inches apart. So how far apart are they in miles? So we know the number of inches on the map. We need to figure out the number of miles in real life. So we have that 2 inches represents 120 miles. Okay. We also know that for the second piece of information, 2 cities are 5.5 inches apart. What we don't know is how many miles is that. All right, so we have the piece of information given to us completely. 2 inches represents 120 miles. We set up a rate, inches on top, miles on the bottom. We now know that 2 cities are 5.5 inches apart. We don't know how many miles that is. That's what we're going to find. So we set up our second rate, 5.5 inches over X miles. We're now good to cross multiply and solve. So I get 2 times X equals 120 times 5.5. As long as you show your steps, I'm okay with using a calculator for some of the smaller calculations. So 120 times 5.5 is 660. Now at this point, we have an equation. We need to solve for X. That means get X by itself. So looking at X, we can see that X was multiplied by 2. I need to undo the multiplication of 2 and X. And I need to remember to maintain equality. So if I do something on the left, I need to do the same something on the right. On the left, the 2's cancel, leaving me just 1X. And then on the right, 660 divided by 2 is 330. Well, 330 what? Go back to the problem. What was X? X was the number of miles apart 2 cities are. So we would say these 2 cities are 330 miles apart. And that's it. I would say out of all of the word problems you're going to do in your math career, proportions are some of the easiest. All right. Let's keep working. So in this case, we have for every 30 attempted free throws, a basketball player can make 23 of these shots. In the I spelled remaining wrong. Forgive me. Let me try that again. In the remaining, I hope I can get it to fit. In the remaining games of the season, this player attempted 180 free throws. How many shots were successful? So we know that out of every 30 attempted, a basketball player can make 23. Okay, so I'm going to go ahead and say 23 successes out of 30 attempts. All right. Now, the second piece of information is not given to us completely. For the second piece of information, we know this player attempted 180 free throws. How many of those were successful? So assuming this consistent rate, there were 180 attempts. And we need to figure out how many successes. Since we don't know how many successes, we're going to assign the variable x to that. So again, first piece of information, for 30 attempted free throws, 23 were successful. For 180 free throws, we need to figure out how many were successful. All of our units line up horizontally. We're good to go ahead and cross multiply. So let me go back to black. So 30 times x, I always multiply so that the x is going to be multiplied first. So 30 times x is going to equal 23 times 180. So 30x equals, let's see what 23 times 180 is. 23 times 180 is 4,140. We have an equation now. So just like in all the previous examples, we need to get x by itself. Since x was multiplied by 30, I need to undo that multiplication of 30. Mathematically, I do that with division. To maintain equality, I'm going to do the division by 30 on both sides of the equation. Note that the sides of the equation are split by the equal sign. The equal sign splits left versus right. On the left, the 30s cancel, leaving 1x. And then on the right, I just have 4,140 divided by 30, and I get 138. Yeah, 138 successful free throws. Remember, with word problems, you never just leave a plain old number. 138 what? 138 successful free throws. And that's it. Let's look at another one. Okay, so for this one, we're looking at gas mileage. So in a small sedan, you can travel 164 miles on 7 gallons of gas. How many gallons of gas would be needed for a 525-mile road trip? Well, we know 164 miles can be driven on 6 gallons. Well, rather 7 gallons. So 164 miles for 7 gallons. All right. The second piece of information is not complete. We want to know how many gallons would be needed for a 525-mile road trip. So for 525 miles, that will go on the numerator because miles are in the numerator in the first rate. So we're going to get 525 miles over X gallons. We got to figure out how many gallons will be needed for this particular road trip. So I've set everything up. Units line up horizontally. I'm good to go ahead and cross multiply. All right. So I get 164 times X equals 7 times 525. So I'm going to get 164X equals, well, 525 times 7 is 3,675. So I've got my equation. I need to get X alone. Remember, when you're solving these equations, your goal is to get X alone. And the way we get X alone is we undo what has happened to X. Well, what has happened to X here? It was multiplied by 164. So I'm going to divide by 164. And to maintain balance or equality, I'm going to divide by 164 on both sides of the equation. On the left, the 164s cancel, leaving me just 1x. And then on the right, 3,675 divided by 164. I get kind of a nasty answer, so we're going to round. Let's say we round here to the nearest tenth of a gallon. So what I get on my calculator is 22.40853659, and then my calculator kind of stops there. So let's say we round to the nearest tenth. All right. If I round to the nearest tenth, I'm going to look one digit to the right of that. Well, that digit to the right is a 0, which tells me to round down. So I'm going to say we're going to need approximately 22.4 gallons of gas. Anytime you round, make sure you use that wavy equal sign. That just tells the reader, hey, I rounded here. This is an approximate answer, not exact. And there you have it. Let's keep working through these. I think we have 5 or 6 more examples. Okay. All right, so for this one, we have a company that manufactures computer chips found that 10 out of 100 of these computer chips are defective. In a shipment of 6,100 computer chips, how many can we expect to not be defective? You get some water here. So what we know is 10 are defective out of 100. That tells me that 90 are not defective. And we kind of have to look at what the question is asking us. The question wants to know how many are not defective, okay? So we already know that 10 out of 100 are defective. That means 90 are not defective. So 90 out of 100 are not defective. We then have, in a shipment of 6,100 chips, how many can we expect to not be defective? All right, so this one's a little tricky because you're given one set of information and then you're given kind of the opposite question to answer. So if 10 are defective, that means 90 are not defective out of 100 chips. All right, and we want to figure out how many are not defective. So X that are not defective out of a shipment of 6,100 chips. All right. So again, this one is a little weird because we're given how many are defective, but the question is asking how many are not defective. You can either do the subtraction at this point and then go ahead and solve for not defective, or if you wanted to, you could have set it up 10 defective out of 100 chips and then found X defective out of 6,100 chips and then done a little subtraction problem. Okay, so there are 2 ways you could approach this one, but I went ahead and did the math now. I went ahead and figured out how many are not defective out of 100, and then we're going to solve from there. So I'm going to cross multiply. So I get 100x equals 90 times 6,100. So I get 100x equals, let's see what 90 times 6,100 is. It's 549,000. I've got my equation. I need to solve for x. I solve for x by undoing the multiplication here. So I divide by the coefficient of x. That's just the number multiplied by x. On the left, the hundreds cancel, leaving me with just an x. And then 549,000 divided by 100 is going to be 5490. A 0 cancels twice, top and bottom. So this tells me that 5,490 are not defective. All right. Now, if I had gone over here to this little side area that I just created, okay, so let's say we were looking at this. We could have solved it this way. I would have gotten 100x equals 10 times 6,100. So that would give me 100x equals 61,000. I would still divide by 100. And x would equal 610 that are defective. Now the question asks how many are not defective. So what we would do is we would take 6,100. We would subtract the defective computer chips. And we should get 5,490. So either way, you're going to get 5,490. It just depends on if you want to do this subtraction at the beginning, like we did here, or at the end, like we did in this little bit of side work. So definitely 2 ways to approach this problem. They're both the exact same amount of work. All right. It's not like one is easier than the other. Okay, it's just how you decide to approach this. All right, either way, again, 5,490 of the chips should be good to go. 610 could be expected to be defective. Let's look at the next example. This one's an easy one. I find a lot of times the fewer words in the word problem, the easier the problem appears. Okay, a lot of us just get lost in the reading and the reading comprehension, but this one should be pretty easy. We have a 36-foot cable weighs 171 pounds. We know that without a shadow of a doubt. So 36 feet, 171 pounds. All right. Now, the second set of information, we're not given exact. All right, we're given partial information. We want to know how much will a 40-foot cable weigh? Well, we want to make sure our units line up horizontally. So 40 feet goes in the numerator. And then in the bottom, X pounds. We don't know how much this is going to weigh, but we are going to find out. All right. So we took the information, we set up two ratios or two rates in this case. The units line up horizontally. At this point, we are good to cross multiply and solve. So I cross multiply. So I'm going to get 36 times X equals 40 times 171. 40 times 171 is 6,840. We've got our equation. We need to get X alone. To get X alone, we undo what has happened to it. So since it was multiplied by 36, the opposite of multiplication in math is division. So we're going to divide both sides by 36. That maintains the equality. On the left, the 36's cancel, leaving me with just a single X. And then on the right, 6,840 divided by 36 is 190. Now, what in the heck is 190? Remember, never just leave plain old numbers. Don't assume your reader knows what 190 represents. We go back to the problem. 190 represents the weight of the cable. So we would say 190 pounds. And that's it. Sorry, my phone is ringing. There we go. All right, let's look at another one. We're going through these pretty quick. All right, so for this one, it has been found that adults should drink 60 ounces of water for every 100 pounds of body weight. At this rate, how much should a 145-pound woman drink? So breaking up this information, we found that there should be 60 ounces of water consumed for every 100 pounds of body weight. So set up your rate. I'm going to put ounces of water on top, body weight on the bottom. All right, so we know that according to this, 60 ounces of water should be consumed for every 100 pounds of body weight. The second set of information is at this rate, how much should a 145-pound woman drink? Well, we don't know how many ounces of water. That's what we're looking for. But we do know the weight of this adult. This is a 145-pound woman. All right, so we read through the information. We found our two rates. We set up the rates so that units line up horizontally. We're now good to cross multiply and solve. So I'm going to cross multiply like this. I'm going to get 100 times X equals 60 times 145. So 100X equals, let's see what 60 times 145 is. We get 8,700. We divide by 100. Remember, we're trying to undo what has happened to X. Our goal is to get X alone. X was multiplied by 100. We undo that by dividing by 100. But to maintain equality, if you do something to the left, do the same something to the right. So we divide both sides by 100. On the left, the 100s cancel, leaving just X. And then on the right, we divide and we get 87. 87 what? Well, this woman should drink 87 ounces of water. This is not exact science, FYI. Okay, this is just a made-up word problem. So don't go out and freak out about drinking your 60 ounces of water for every 100 pounds of body weight. All right, next problem. For this one, it says a standard dose of a medication is 4 milligrams per 50 pounds of body weight. How much of this medication should a 180-pound man take? Well, let's look. According to this, the medication recommends 4 milligrams per 50 pounds of body weight. So we'll start there. I'll do milligrams over weight. All right. The second piece of information is incomplete, but it tells us or asks us how much of this medication should a 180-pound man take? Well, we know the weight of this person, 180 pounds. What we don't know is the number of milligrams of this medication. So we read through the information, we found our two rates, we set our two rates equal to each other in such a way that common units line up horizontally. We're now good to cross multiply. So I cross multiply, I get 50. That looks kind of crazy, hold on. I get 50 times x equals 4 times 180. So I get 50x equals, let's see what 4 times 180 is. 4 times 180 is 720. So then at this point, I've got my equation. I need to get x alone. X has been multiplied by 50. I have to undo that multiplication with division, and I have to do it on both sides to maintain equality. The 50s cancel. And then 720 divided by 50 gives me 14.4. Now, what was 14.4? 14.4 represents the number of milligrams of this medication. So this particular 180-pound adult should take approximately 14.4 milligrams of this medication. Remember, never just leave an answer alone when you're dealing with a word problem. You have to describe that number. All right. So I think we have maybe 3 more examples. I lied earlier. I think we had 6 or 7 left when I said 5 or 6. Okay. So this is a really classic example, and this is very useful for any of us that work, okay? All right, James can make $199.50 if he works 14 hours. How much will James make during a 40-hour work week? Well, we already know that if James works 14 hours, he's going to make $199.50. All right. Whether this is before taxes or after taxes is irrelevant. We're just interested in flat numbers here. So $199.50 can be made in a 14-hour shift or during the course of 14 hours. How much will James make during a 40-hour work week? Well, we know the number of hours. So we're going to line that up in the denominator like we have it in the first rate. What we don't know is the dollars. So James is going to make X dollars if he works 40 hours. So we took the information from this word problem. We set up our two rates. We have them set up so that units line up horizontally. Now we can cross multiply. So I'm going to get 14x equals 199.50. I just saw a tiny mistake here. Not supposed to be a 5. All right, so 14x times equals 199.50 times 40. So 14x equals, well, let's see what 199.5 times 40 is. I get 7,980. But I need to undo the multiplication of 14 and x, so I'm going to divide on the left. That means I also have to divide on the right. Over here on the left, the 14s cancel, leaving 1x. And then 7,980 divided by 14 is 570. Well, what in the world is 570? That's $570 for a 40-hour work week. And that's it. Not bad. Okay. So hopefully these are getting easier the more you do them. Once you get the hang of setting up a proportion word problem, it's really, really not bad. Solving is pretty straightforward. Okay, 2 more problems. So in this case, it says a study found that 2 out of 9 people prefer to take night classes over day classes. All right, so think college students, some of them like night classes, maybe they work during the day, maybe they have kids, whatever, but 2 out of 9 people prefer night classes over day classes. In an orientation of 180 people, how many would prefer day classes? So this is like one of those earlier examples where we were given one set of information, but asked to answer a different set of information. Okay. So in this particular case, we know that 2 out of 9 like night classes. So that means 7, the remaining 7 out of 9 people prefer days. And I do this because we're interested in people that prefer day classes. Okay, so this is like that example with the computer chips, and some were defective, some were not defective. And we had to figure out what we were being asked. We were asked how many were not defective. So in this case, we're asked how many prefer day classes. So I'm going to go ahead and do my math right here. 2 out of 9 people like night classes. That means 7 out of 9 like day classes. Okay, so we know out of 9 people, we have some that prefer nights, but I'm going to go ahead and switch it to days. And then we're looking at an orientation of 180 people. How many would prefer days? Okay, so I've got 7 prefer days out of just 9 people. And then we're going to find how many prefer days. We don't know. Out of 180 people. We've got an orientation with 180 people. We want to see, assuming this same rate, 7 out of 9 people prefer days, how many in this group of 180 people will also prefer days. So we're ready to cross multiply. So I'm going to get 9 times x equals 7 times 180. So 9x equals, let's see, 1,260. I need to undo the multiplication of 9 and x. We undo multiplication with division on both sides. On the left, the 9s cancel. We get really lazy a lot of times in math, and I've been very lazy in this video. We say, oh, these numbers just cancel. Well, in math, numbers only cancel 2 ways. They either cancel with addition and subtraction to be 0, or they cancel with multiplication and division to be 1. So when I take this 9 and the 9 in the denominator, and I'm like, oh, they cancel. That's because 9 divided by 9 is equal to just 1x. Now, 1260 divided by 9, I get 140. So what does this mean? We can't just leave it plain old 140. We have to go back to what the question asked. The question asked how many students prefer day classes. Well, this means 140 people prefer days. Now, let's pretend you didn't do this right here, where we were given information about how many students prefer nights, but we flipped it and we figured out how many prefer days. Let's say you just kept it with the original information. We would have gotten 2 prefer nights out of 9 people. So we would have X nights out of the 180 people in the orientation. We will get 9x equals 2 times 180. 9x would equal 360. Divide by 9, divide by 9. So in this particular case, the 9s again canceled, equal 1x. And then 360 divided by 9 is 40. All right, but what is this? 40 that prefer nights, but that's not what the question asked. The question asked how many prefer days. So we would have to take the 180 people at the orientation, subtract the 40 that prefer nights, and we would still get 140 prefer days. So it doesn't matter how you approach this. At some point, you're going to solve a proportion, and there's going to be a little tiny bit of subtraction involved. Either do the subtraction right off the bat. If 2 people out of 9 preferred nights, that means 7 out of 9 prefer days, and then set up your proportion, or set up your proportion with the information given. Just make sure you go back and do the subtraction to figure out how many people prefer those day classes. Okay, so again, this is just like the computer chip problem. You could solve it 2 ways. Either way, same amount of work, you're going to get the same answer. All right, last problem, and this one has several things going on. Okay, so let's read it carefully and then we'll get started. So we have that a 40-pound bag of fertilizer costs $7.25 and covers 2,500 square feet. Okay, this is all made up information. I didn't go to Lowe's and look it up. I stole this from another textbook. Okay, so a 40-pound bag of fertilizer costs $7.25 and it covers 2,500 square feet. How many bags would be needed to fertilize a yard that measures 275 feet by 180 feet? And then what would this cost? So we have a lot going on here. And the most important thing that we have to do right off the bat, before we even get to the proportion, we need to figure out how big this yard is. So we're going to look at this information right here. We want to figure out the area of this yard. Well, area is length times width. Okay. We're told that the length of this yard is 275 and the width is 180. So 275 times 180 is 49,500 square feet. So that's what we're dealing with for our yard. It's very important, okay? Because the amount of fertilizer or the bag of fertilizer is given in how many square feet it covers. Our yard or our garden or our field, whatever we're dealing with here, measures 49,500 square feet. So what we need to do now is figure out how many bags of fertilizer. We know that one bag of fertilizer, so one 40-pound bag of fertilizer, costs $7.25, but most importantly right now, it covers 2,500 square feet. So this information, we don't need all of it. We need that one bag covers 2,500 square feet. So we've got one bag and it covers 2,500 square feet. Well, we need to figure out how many bags are going to cover 49,500 square feet. Okay. So instead of using the dimensions of the yard, we're going to use the actual area of the yard. So 49,500 square feet. So how many bags are we going to need first? Okay, so we'll go ahead and solve this proportion. I cross multiply and I get 2,500x equals 1 times 49,500. I need to undo the multiplication here. So I'm going to divide both sides by 2,500. On the left, the 2,500 cancel to give me 1x. And then 49,500 divided by 2,500 is 19.8. Now, here's the deal. Can we buy 19.8 bags of fertilizer? No. Okay, Lowe's, Home Depot, Ace Hardware, wherever you're going to get your fertilizer, they're not going to crack open a bag and give you 0.8 bag. So what we need to do is we're going to always have to round up to the next bag. So we're going to have to buy 20 bags. We'll just have a tiny little bit left over. Okay, so we need 20 bags. Now we need to figure out the cost. So for the cost, we're going to take our 20 bags and we're going to multiply it by the $7.25 for the cost of each bag. So on my calculator, I'm going to take 20, I'm going to multiply it by 7.25, and I'm going to get that it's going to cost $145. So here's how I would wrap this up. We need 20 bags of fertilizer for a total cost of $145. You always need to wrap up your word problems, okay? As a math teacher, I can generally follow your work and I know what you're talking about, but never assume your reader has any kind of math background. So if a reader looked at this slide right here, they'd be like, what in the heck is going on, right? So they could see our work over here where we found the area. They could look over here and figure out where we found the number of bags. They could look over here and figure out the cost, but they may not be able to put it together. It is your job as the presenter to put together your total findings. We need 20 bags of fertilizer for a total cost of $145. All right. So there you have it. Let me stop share. Okay, so that's the last video in this series on rates, ratios, and proportions. So in this video, we just talked about solving word problems. I encourage you when you watch these videos, don't watch them blindly, work the problems out with me. So if you've already watched this and you didn't work the problems out yourself, go back, get out a piece of paper, watch the videos, pause them, solve the problems, and then wait to see how I solve it to make sure you're good to go. Next series of videos will be on percents. So make sure you know how to solve proportions because that will be helpful later when we look at percents. All right, take care.